Section 1.4, we're going to talk about continuity and one-sided limits. Now, we've already talked a little bit about this. In fact, the quiz question that I just went over about the graph, it had this exact issue with it, right? It had the issue where there was this jump in the graph, which means there was something that's breaking the continuity, and we looked at the individual limits from each of the individual sides. So we're just going to continue along that idea with this lesson. So to start with, continuity at a point. So a function is continuous at C when the following three things are all true. The function has to be defined, so I have to have a filled in circle. Okay, so it can't have an asymptote there, it can't have an open circle with a not filled in. Okay, those are the things it can't have. The limit has to exist, which means from both directions we have to approach the same value. That's actually where your problem on your quiz failed. And the value that it approaches has to be the same filled in value that you got from part one. They have to match. So in other words, what you can't have happen, I'll just draw you a picture of what's not possible. You can't do this. That's not a very good picture, but you have the right idea. Where there's a closed in circle, there's a limit for both directions, but they don't match. Okay, so this is a no-go. That's what C, or 3, part 3, guarantees is not okay. So this is continuity at a very specific point. So that problem that we had on the quiz, it was continuous at a lot of points, just not at the point X is approaching 2, or I think it was, or whatever it was. Right? That location, or 1, whatever. That location it was not continuous at. But we can also talk about continuity on an open interval, like on a bunch of data values. So a function is continuous on an open interval when it's continuous at each point in the interval. Seems reasonable. And if it's continuous on the entire graph, right, from negative infinity to infinity, we call it continuous everywhere. Something else you'll sometimes see is you'll see the language continuous on its domain. We don't use that one quite as frequently, but that is another possibility too. Now the cool thing is that in spite of the fact that we're looking at limits from the left and from the right, most of what we've done when we were looking at limits at just any particular value, regardless of the left or the rightness, it all still works. So for instance, on this one, it says that we're trying to find the limit as x approaches 8 from the right of 1 over x plus 8. But the x from the 8 from the right, that plus sign, it's actually quite irrelevant. We can still attempt, if possible, to plug in 8. And if it works, that's still going to be our limit. So as we're looking at this problem, just like we did in 1.3, we're going to attempt to evaluate it at the limit, or at the value x is approaching. And this one works just fine, and we get 1 over 16. It's not any different than if the plus had not been there. Now the second one, we're going to try the same thing, right? We're going to plug in the number again, 9. It's not negative 9. It's 9 from the left, so it's a 9. So we have the square root of 9 minus 3 over 9 minus 9. And what happens? 0 over 0. We saw that happen last time, right? It's a very special case. 0 over 0 means something can be factored or reduced or simplified so that I don't end up with 0 over 0. Still might have a 0 somewhere, just not in both the top and the bottom. So this one has a radical involved, right? And we encountered that last time. Do you remember what we had to do in order to simplify? Because factoring doesn't work here. We need to get rid of the radical. So we use the phrase rationalize. And since the radical's in our numerator, we're going to rationalize the numerator. Now, do you remember how to rationalize? How do we get rid of that square root? Okay, so we encountered this verb, or not verb, noun, last time, and it was the word conjugate. Do you remember that one? So conjugate has the same values, it just has a different sign in the middle of the part that has the radical in it. So I have the square root of x and I have the 3, but it's addition. And I do the numerator and the denominator, of course, when I multiply. So it's all about conjugates. Now, the denominator, like last time, I don't really want to reduce or simplify anything. I really would kind of like to leave it in factored form. Okay, so it feels a little bit like, well, didn't I just rewrite it? Well, yeah, you did. But that's going to be the most helpful way to continue in the problem. It's not to simplify or distribute or anything here. But the numerator is good stuff, right? So I told you last time that the reason this whole idea of conjugates works is because we've really got a difference of squares. So I end up multiplying the first two terms together. So what's the square root of x times square root of x? X. And I multiply the last two terms together, which gives me a -9. And that's really all I have to do, because if you take a careful look, the inner term and the outer term, that's not a good color. Let's try something else. How about green? The inner term and the outer term, they match, right? But one's a positive and one's a negative, so they add to 0. So multiplying by conjugates always gives us just the first term times itself and the last term times itself with the opposite sign. And do you see why I did not want to multiply out the denominator now? Yeah, they match with the x minus 9s, right? The entire piece, the entire thing matches. Can't do that if I've got addition and subtraction and it doesn't completely match. But this one does. So what am I left with on top? A 1. And the denominator, it still has radicals in it, but it's radicals with addition, which is a lot more friendly because I'm able to evaluate those. So now I have 1 over the square root of 9 plus 3. So what's the square root of 9? 3, right? And then plus the 3 that's on bottom gives me a 6. So I have 1/6 for my limit on this problem. Okay, does this feel a lot like what we did last time? I hope it does. Because so far the only difference has been sort of the little negative that's there and we haven't had to do anything with it. Or on the last problem, the little positive that came after the 8, but that didn't really affect anything, right? Yeah. Okay, let's try another one. This one is actually quite different. What about this makes it different? Y'all know. Those absolute values are something different. We haven't done anything with the absolute values, right? And you may remember what graphs of absolute values look like. You may not. You could do it from a perspective of a graph here, and it would be okay. I'd like to do it from a perspective of what an absolute value actually does. So if this is the first place where it matters which side we're coming from. What kind of values do you get if you're considering the values that are to the left of the number 0? Negatives. These are negative numbers. That's really important because negatives and positives do different things when they're inside of absolute values, right? What's the absolute value of 5? 5, right? If it's a positive number, then an absolute value doesn't actually give you any different value. But what happens if you've got the absolute value of -5? It's positive 5. The sign changes, doesn't it? So that's what's going on in this problem that makes it really matter. So on this one, I'm looking at values that are negative. And if the absolute value of x has inputs that are negative, then the signs change, right? And the way we write that is that whatever the x value was before, now it's the opposite. And so it looks like I'm putting a negative on it. But remember, it's because x is itself a negative number. So think about what would happen. I used number 5 here. What is the opposite of -5? It's 5, isn't it? So that's why this symbol or this notation actually makes sense. It's because it's just changing a sign and the x values themselves are negative. So when I'm dealing with this particular problem and I'm looking at the limit as x approaches 0 from the left, the numerator is going to change signs because I'm dealing with absolute values of negative numbers. And the denominator is just x. Now, it's still clear, and I didn't do it above because it was talking about what happens with the absolute values, but if you had tried to do this, you would get 0 over 0, right? Are you with me? Okay. So the same's true down here below. I have negative x over x, and if I simply try to plug in 0, I get the opposite of 0, which is still 0 over 0, and I've still got a problem. But it's kind of okay, because what can I do with negative x over x? The x's cancel, right? I can reduce it. X over x is 1, and I've got a negative on top, so this is actually the limit as x approaches 0 from the opposite side, or from the negative side, of negative 1. And what's the limit of negative 1? Negative 1. Just for the reference point, I'd like to draw you a picture of what it does look like if you put it into your calculator. If you really want to see the calculator and how to put this in and you don't know how to put absolute values in, come see me later. I'm happy to show you. But if you were to able to put this in the calculator, it would actually look like this. That's what you would see. You'd see a positive 1 on the right, and you'd see a negative 1 on the left-hand side of the graph. So the reality is that this one is the closed circle, and this one is an open circle. But as you're moving towards this direction, right, the y value you're approaching, and you're actually at it, is negative 1. So that's from a graphical standpoint. You'll notice the directions up here didn't say how do I have to do the problem, did they? So we did it algebraically, in part simply because that's usually the quickest and cleanest way to do it. But you don't have to. If you really like doing a graph and you can justify with a picture for me in a graph, that's acceptable. Or if you liked the tables, if they sort of made conceptual sense and you want to draw me a table and the directions didn't say you can't do that, then you can do a table. Okay? So there's more than one way to do these problems. I'm just showing you one. Okay, so we have encountered in both problems 2 and 3 above 2 different kinds of discontinuities. One of them is called removable. Removable occurs when f can be made continuous by appropriately defining or redefining the y value. Visually, removable discontinuities happen when you have holes. If there's a hole in the graph, if there's this cancellation happening and things get removed, right? The absolute value one's a little different. But the second problem that we did with the rationalizing, there's a hole in the graph. That's why that's happening. The second type is called non-removable. Non-removable occurs when f cannot be made continuous by appropriately defining or redefining. And this happens when we have jumps. That was what happened on the third problem, right? A jump. Or, and I didn't show you an example of this, but we've seen one before, an asymptote. It's discontinuous, and there's no way to like fill in the hole, right? When I have a hole, I could just give some kind of a definition that changes it and it fills in the hole. And if I could fill in the hole, everything would look just dandy, right? But I can't do that if I've got a jump in the graph. There's no single hole to fill in that makes me not have to pick up my pencil. So I have a non-removable discontinuity. So on 4 and 5, the problems are going to be quite similar to what we've seen before, but we're simply going to be doing a little bit different in terms of the directions. Are there any questions about these continuities before I switch slides? Okay. So our directions say find any values where it's not continuous, and then which type of discontinuity, or which of the discontinuities in number 4 and number 5 are removable. And we're going to go a little bit further in our notes just so that as you reference back, you'll have a reason why it is or it isn't, why it does or doesn't work. So in particular, when it asks you about discontinuities, places where it's not continuous, you're looking for a couple of things. Usually you're looking for places where denominators are 0, to be perfectly honest. And that's pretty clear on this one. Where is this denominator going to be 0? At what x value? At 0. So this is not continuous. At x equals 0. And when we get to number 5, we'll have to do a little bit more work to figure out where it's not continuous. But this one, it's pretty clean. And then we're supposed to decide if it's possible to actually remove that discontinuity. So when is it possible to remove a discontinuity? Well, in particular, when things cancel out. There's no way to cancel that x in the denominator out, right? Now, pause for a moment and consider. Don't write this down, but just think with me. If this had been my function, 6x over x, you'd still have a discontinuity at x equals 0, okay? Still can't have 0 in the denominator. It would still be a problem spot. But would it be removable? Yeah, because I could cancel the denominator x out. I could change the function to simply be f of x equals 6, and it would be defined and fine and everything would be good. But I don't have that, right? I don't have a way to cancel out the x, so this is non-removable. And I'm going to put this here as a reminder. You might want to write it down. It's because the x on bottom doesn't cancel out. And in particular, what that means, based on the things we looked at on the previous slide, is there's an asymptote. So I realize the question didn't ask for all of that, but I'd like for you to be able to look back at this and try to remember why we made that decision. So let's take a look at one that looks a little more work. It looks like a little more work. It does. Still the same directions. Find the discontinuities. So discontinuities happen in large part when the denominator is equal to 0. So we need to figure out what the denominator values would be that would give me a 0 in the denominator. And that in particular often means factoring. Sometimes it doesn't. Sometimes it's actually the the rationalization pieces, but most often it's factoring. So how will this denominator factor? X minus 5x plus 2. Is everybody good with that? Awesome. Now you see something canceling out, right? And we'll do that in a minute. But the first question is simply, what values for x make it discontinuous? Or equivalently, what values for x make the denominator 0? So it is not continuous where? Okay, so it's at x equal 5 and at x equal negative 2, right? I know I'm going to be canceling out the negative 2 in a minute, or the x plus 2, I get that. But it's still a discontinuous location because I cannot have x equal negative 2 in the original problem and actually get something that works, okay? So it's still a place of discontinuity. However, like we mentioned before, this does cancel, right? And since it's canceling or able to be removed from being a problem, it is a removable discontinuity. So I have a removable discontinuity at x equal negative 2. And visually speaking, that means there's a hole in the graph. And I have a non-removable discontinuity at x equal 5. And again, that means I've actually got an asymptote there. Any questions on that? always the denominator. So if I had other things in the numerator, like let's say the numerator factored, it had like a polynomial in it as well, like a quadratic or something, and it factored, all the pieces of the numerator are irrelevant to the discontinuities, but they are relevant if they cancel out to making them removable or non-removable. Yeah, exactly. All right. So when then does a limit exist? Well, let's let f be a function and c and l be real numbers. The limit of f of x as x approaches c is equal to L if and only if the limit from the left is equal to L and the limit from the right is equal to L. So we've already seen that, not in so many words, but in the graph that you just did on your home or your quiz. When the limit from the left and the limit from the right don't match, the limit doesn't exist. When they do match, it does exist. So on this problem, we're going to be doing something a little bit different. First of all, the problem is piecewise defined. Okay, so the graph looks like 3x squared when you have values that are greater than x equal 1, and it's going to look like ax minus 4 when you have values that are less than negative 1. So 3x squared is a parabola, and ax minus 4 is a line, right? And they're changing the definition of what the function looks like at the specific point x equal to 1. So you have something like this going on. At x equal to 1, on the right-hand side of x equal to 1, there's some portion of a parabola. I know it's a parabola opening upward because it's 3x squared, right? So it looks something like that, maybe. And it's clear and defined, and your graph could do it for you, no problem, your calculator, no problem. But the other one, ax minus 4, well, a is a number, but we don't know what number it is. So yes, I have a line, but maybe the line looks like this, and there's a jump right there. Or maybe the line looks like this, and there's a jump. Or maybe the line looks like that, and there's a jump. I don't know. But what I really want to do is I want there to be a way that I can sort of take whatever that line is and shift it up and down so it matches, and I end up having something like that. Are you with me with the goal? The goal is to take whatever this line looks like and figure out how to make it work so that it actually will hit that red dot. Now, I know a little bit more than I was letting on. I do know that it has a y-intercept of -4, right? I mean, I do know that. So I just have to adjust the slope to make it work is what I really need to do. I need a slope that doesn't look like this, right? I need a slope that looks like this. Are you with me? So how do I get that to happen? Well, what I really want is I want the limits from both directions to be the same, right? That's what this said over here. The limit's going to exist if the limit from the left and the limit from the right match. So I'm going to find those two individual limits. So we're going to look at the limit as x approaches 1 from the left. That's the ax minus 4. And we're going to look at the limit as x approaches 1 from the right. That's the equation 3x squared. So if I plug in the number 1 into ax minus 4, what will I get? I know it's not just a number. I get that. A is still going to be in it, but what's it going to be? A minus 4, right? A times 1 minus 4. I have a minus 4. If I plug in the number 1 into 3x squared, what am I going to get? Not 9, close, 3. Remember, the 3 doesn't get squared, just the x does. Yeah. So 3 times 1 squared, 1 will be squared, so I get 3. Everybody good so far? I have found the individual one-sided limits. One of them still has this random a in it. I get that. But if I compare them now, and I want them to be equal, I should be able to find a number that works. What value does a need to be? A needs to be 7. If a is 7, then this will work. Now also, I'm not going to take the time because I don't really think it's all that helpful in general, but your calculator can graph piecewise functions. If that's something that you feel personally would be very beneficial or helpful to you, come see me. I'm happy to show you how to graph piecewise functions, especially if you're a real visual person. And if you're not, then I don't want to take your time to do that. But your graph can show you that this actually would give you the right answer too. And that's what we're supposed to do, find the real number A. Any questions on that? All right, so we did continuity at a point. We did continuity on an open interval. Now this is the definition of continuity on a closed interval. And you'll notice that it's mostly the same with a little bit extra at the end. A function f is continuous on the closed interval ab when it's continuous on the open interval ab. And the limit as x approaches a from the right is f of a, and the limit as x approaches b from the left is f of b. The function is continuous from the right at a, the function is continuous from the left at b. So all that's saying is that the end points of your interval, whatever's happening, aren't going to be, asymptotes or jumps in graphs and things like that. There's actually a value at the end that's equal, closed-in circles kind of things. Starts and stops, there's no ambiguity on the end points. That's all this is saying. And everything else happens in between the same way it did before. Nice and smooth and all that good stuff. Theorem 111 talks about 4 properties of continuity. And we've seen these 4 properties of limits. And continuity is all about limits. So it makes sense that these are the same. They look just like what we had seen before, but in a maybe cleaner fashion. If b is a real number and f and g are continuous at x equals c, then the functions are also continuous. If I have a continuous function and I multiply it by a scalar, it's still continuous. If I have 2 continuous functions and I add or subtract them, it's still continuous. 2 continuous functions and I multiply them, still continuous. And if I divide them, still continuous as long as the denominator is not 0. We saw all these same properties when we looked at limits. Okay, there's one more interesting topic in this section. Is everybody good on this slide? Okay. And this is the idea of an intermediate value theorem. If f is continuous on the closed interval a, b, and the endpoints don't match, that's what f of a not equal to f of b means. They're at different heights. If k is any number between f of a and f of b, then there exists at least one number c on the interval ab such that f of c is equal to k. It feels super wordy, but it's one of those, well, duh, when I draw the picture. Are you ready? Okay. So just as a reference point, let me draw a axes. And we're going to mark a point A and a point B. And what it says can't happen is that the y values at A and B can't be the same. So it doesn't really matter which one I mark higher or lower, but they can't match. So far, so good? So I've got something happening between A and B, and it's continuous, because that's what it said. Okay, it's continuous. So over here is f of A. Over here is f of B. And they're saying if k is some value between f of a and f of b, then there's no way to start at f of a and get to f of b, and not actually hit a height of k. Has to happen. Somewhere along the way, there was a y height of k. And it happened at some location c between a and b. And the reason that works is because it's continuous. So what can't happen is you can't do something like this, right? can't just jump across k. Right? This is not, no jumping allowed because it said it's continuous. Right? I can't do that. So somehow, if it's continuous, it crossed right there, and that was my height of k point with my c value down below. There are some conditions that make this work. F has to be continuous. The endpoints can't match. And the k value has to be between those y values. Those are the three conditions. So as long as those three conditions hold, then the rest of the theorem follows. So when we're asked on example number 7 to verify the intermediate value theorem, we're asked to verify that those three conditions hold. So again, condition number 1 is that we have to verify that it's continuous. Condition number 2 is that we have to verify that f of b does not match f of a, or f of a does not match f of b. And then the third thing is that we have to verify that this k value is between them. And it might be like that, or it might be that f of a is the smaller one and f of b is the bigger one. I didn't say that right. The f of a is the bigger one and f of b is the smaller one. But these are the three things we have to verify every single time. Okay. Now, the very cool thing on number 1 is that you usually get it for free. You still have to tell me it's true, though. Okay, so this is a continuous function. It is. Why? Any ideas? It's a parabola. And even more generally, all polynomials are. So there is a theorem in your book that says if it's a polynomial, it's continuous. So we get this because it's a polynomial. But you have to tell me that on your paper. So if you're doing a quiz question on this, you have to tell me that this is why you know it. All right? Don't just gloss over that one. That's a really easy thing that people sometimes forget to say. The second one is that f of a does not equal f of b. Well, the a and the b in this problem are right here. And I don't need to know that a does not equal b. I need to know that f of a does not equal f of b. So in particular, I need to find out what is f of 2 and what is f of 3, and I need to verify that they don't actually match. So I need to do 2 squared minus 7 and 3 squared minus 7. So what is 2 squared minus 7? It's what?
-3.
Negative 3. And 3 squared minus 7? 2. And do these match? Nope. So these are not equal. So that's sort of like check step number 2. And then the third thing to verify is that the value that I'm looking for, the y value, actually occurs between those two. Right? So this negative 3 is in fact less than the 1, and it is less than the 2. This 1 is in between them, and it is. So that's step 3. So that's the verifying part. And then it says, now that you know that, find it. Because you don't want to go looking for something that doesn't exist. That's often very it's frustrating when you're looking for things that don't exist. You know this is going to exist. It is going to work. So you're going to be able to do the problem. And in particular, then you're going to set x squared minus 7 equal to 1, and there's going to be a solution. So if we add 7, x squared is equal to 8, and we take a square root. What do you have to remember when you take square roots? Plus or minus. The square root of 8 simplified, right, is this 2 square root of 2. Good. Now there are 2 x values here. I'm going to write them out separately, actually. So I have 2, sorry, wrote that wrong. Yeah, 2 square root of 2, and I have negative 2 square root of 2. Which one is actually between the a and b value that I'm given? The positive one, because the interval I'm on is from 2 to 3. And if you aren't sure, you're like, okay, well, obviously it's not the negative one because it's negative. Is it really going to be the positive one? Is it really going to work? You could check by verifying the approximation in your calculator. just so that you know, this is approximately, 2.82. So yeah, 2.82 is in fact between 2 and 3. So this is actually C, the C value I'm looking for. They aren't both. They could be. I mean, I could get two answers and both of them are between my interval. It's possible. This one just didn't. It didn't work out that way, okay? Any questions on that? All right.